Recording. Okay. Good Thursday. Okay. So we're wrapping up this chapter, right? And next Thursday at the same time, right, we're going to have our first midterm, okay, which is going to be 3 problems from chapter 22, 23, 24, okay? And on Canvas, I also made a little discussion board so you guys can post the top 3 questions / concept / example / worksheet thing that you want to discuss on Monday, first 30 minutes of class, right? And that way, before we jump into chapter 30, chapter 25, right, we'll have a little review for half an hour. And, you know, if it goes longer, that's okay. You know, if it's shorter, that's okay also, right? So it's a little bit flexible on that. Any questions or concern about the midterm before we get started today? All right. Okay, so this is something I just kind of want to start doing in this class, especially for you guys, because when I was taking this class with, you know, at my community college back in near Los Angeles, even towards the end of this class, I still have no idea what physicists do. And so I just want to like kind of highlight some people who happens to be born around the same time. So so Faye, I'm not going to try to attempt to pronounce her last name. She was actually born on February 13th, so we're a few days late. But she was a nuclear physicist. That means she studies the nucleus of the atoms, right? And she's actually known for her experimental work in nuclear spectroscopy. I guess we have a couple of physics majors here, but we do this thing called spectroscopy, which is actually the machine like a couple of doors down from here, where you can differentiate different elements, which have also a periodic table up here, right? Different elements in the periodic table, and this was work done, I think, probably back in, you know, the 1940s and 1950s, right? And she was recognized by getting a National Medal of Science in 2008 when she was much older. So this is the way scientists gets recognized when you're really old and you can't actually take advantage of the money that the government with these prizes gives you. That's when they give you the money. Okay, it's kind of interesting that way. But so I'm going to try to give this, you know, kind of highlight this type of work every lecture in the beginning. And so if you have any questions about what she did, how she did it, let me know. Okay. So let's get back to what we need to finish covering before we jump into the worksheet today. Okay. Yesterday I started talking about conductors and insulators. Remember, the idea of an insulator is that the charges, once the charges is deposited there, they're not free to move around. Okay. But a conductor, when the charge is deposited there, even if you put all the charges on one end, they will also actually spread around, right? So the idea of a conductor, like let's say you have a little cylinder like this, right? If I put all the charges on one end, since the charges are free to move around, right? These positive charges are going to repel each other, so they're going to get as far away from each other as possible by somehow me having the magical force to close one note remotely. Let's go back to that. And now it decides to be a white screen. Okay. Very nice. Scroll, 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 scroll. Almost there. Okay, almost there. Come on. Come on. Okay. Did all this scrolling just a few minutes ago. Okay. Anyway, so all these positive charges, right, they're going to spread apart. They're going to get as far away from each other as possible, right? Right? As if, you know, all of us are kind of like stinky from a good, you know, run or playing tennis or something. Everybody's trying to get away from each other at the edge of the room, right? That's what happens to charges in a conductor. What we're going to do today is actually going to combine our knowledge of what a conductor does and what we just learned about Gauss's law, okay? Right? Primarily to figure out actually what is the electric field inside a conductor, okay? So before I show you guys the book picture, right, let's just, take this little blob shape, right? So one of the things we learned about conductor just now, right, is that the charges are going to, if it's charged, the charge is going to get as far away from each other as possible, right? So if I put some charge all in the middle, right, they're going to spread apart, and they're going to get to the edge of this conductor, right? Right. So what happens is that these plus charges will reside on the edge, right? And if you think about this, it's kind of like a three-dimensional object. This is actually the surface of that object, right? So there's a good example here, right? So let's say I'm taking, pretend this is not plastic, it's a conductor, right? If I put some charge in there, all the charges will actually be on the surface of this conductor, right? It's like, oh, that's kind of cool, because they're just trying to get as far away from each other as possible, right? So cool thing about Gauss's law is that you can draw your Gaussian surface to be whatever the heck you want. What I'm going to do is I'm going to draw my Gaussian surface following kind of like right up the contour of this little blob shape, okay? Okay, this is my Gaussian surface, right? If I want to figure out the electric field on this Gaussian surface, right, let's say over here, right? Well, let's not even draw the direction, because it's actually going to be inaccurate if I did that. Okay. Say I want to try to figure out the electric field on that Gaussian surface. I use Gauss's law, right? So let's just do the electric flux equals to E dot dA, right, equals to the charge inside that surface, okay? What is the amount of charge inside that surface on a conductor? If all the charges has to move to the edge. I draw this little line just so it's not on the surface. It's either 0 or not 0. Which one it is? Not 0. It's what? Not 0. Not 0. Remember the idea of charges on the conductor is that they're going to get as far away from each other as possible, right? And so all the charges going to reside on the edge of the conductor. So just from this drawing, is there any charges that's inside this orange line? No. So the charge enclosed is actually 0, right? Which is kind of neat, right? If we know the charge enclosed is 0, right? That means either the electric field is 0 or the area of this surface is 0, right? Remember, one of the things with math is that if you have A times B, if that's equal to 0, either A is equal to 0 or B is equal to 0, right? From looking at this drawing, right, the surface area of this little weird amoeba shape, right, that's not 0, right? This cannot be 0, right? Therefore, the electric field has to be 0, right? It's kind of neat. So anywhere on this surface, right, I'm just going to do the red dots, right, at this point, 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 anywhere on this surface, we know that the electric field is actually 0, okay? Right? I can draw another Gaussian surface. Let's draw that a little smaller, right? Still the same shape. What is the electric field on this surface that I just made up, the purple surface? It's 0, right? So in fact, the electric field inside a conductor is always going to be 0, right? It's just kind of neat, right? And that's what this next picture was able to draw a lot better than me, right? Okay, so this is just by knowing what conductor does and applying the simple case of Gauss's law, right? The amount of charge enclosed is 0, therefore we know the electric field has to be 0. Okay, okay. So this is let's not call it a symmetry. So using Gauss's law, we can tell that there's no charge inside the conductor in this static equilibrium situation, okay? When we get to chapter 27, okay, this is only happening in electrostatic equilibrium. When we get to chapter 27, when we do have charges moving around, we're going to find that that there are cases where the electric field is not zero inside a conductor because the charge is actually moving around. Okay, we're going to get to that later. Okay, so if you have charges moving around, so you don't have to draw this. This is just for kind of like a foreshadowing, right? If you have like a bunch of electrons moving around, right, that's going to produce a non-zero electric field in here. Okay. Okay, but let's just don't worry about that for now. It's just that when you see in the future, it's not a contradiction. Okay, the requirement for the electric field inside a conductor to be zero is this electrostatic equilibrium where the charges stop moving. Okay, these are not moving anymore. Okay. Okay. So let's examine a little bit more detail what happens on the surface of this conductor, right? Since all the charges are on the surface, right, you can try to draw, right, the electric field coming off of the surface. So outside the conductor, there is an electric field. Inside the conductor, there's no electric field. Right, sort of neat. Right, so outside here, right, this electric field has to point away from these positive charges, right? Because none of them can actually, it can never curl back, right? Because remember that electric field always points away from positive charge. Right, it points towards negative charge, right? Okay. So once again, what we're going to do is we're going to do plane. Well, this is going to be the plane symmetry. If I can spell plane, that'll be nice. Okay. Okay. When we think about that, well, this is a very similar situation when we had just a plane of charge. Let me not draw that in the bad color scheme. Let's do that in blue. Come on, blue pen. Don't be mean to me. Okay. Right. Remember in plane symmetry, when you just have charges on the surface. Okay. Okay. Right. The electric field. Let's draw the electric field in black. Right. The electric field is pointing away from the charges. Right. Perpendicular to that surface. Okay. And the electric field on that surface is just the charge density divided by epsilon naught, right? We can apply that same idea here, right? Where even though this is a curved surface, right? If you zoom in close enough to the surface, just like how we, when we're on the surface of the planet looks flat, right? Right, but if you go far away from the planet in a spaceship, that's when you start seeing the curvature, right? When you're very close to the surface, right, what happens is that you can just treat that curved surface as if it's flat, right? Just like the Earth looks flat from when you're very close to it, okay? So you can say that, we can find that, well, the electric field strength here is also the same as if we just have a plane of charge where we can just write down what the answer is, right? It's the surface charge density divided by epsilon naught. And the direction is going to be perpendicular to the surface, okay? Okay. Another word is this n hat factor I showed you guys before, right? That's the normal vector for the surface, okay? So this will have a different n hat, but near the surface here, right, the electric field is going to be, basically you can calculate it by just the charge density divided by epsilon naught. Okay. Any questions about this? About this justification of a curved surface to a flat surface if you're very close to the surface, right? Okay. All right. All right. Now let's do something even more, well, to me more fun, maybe confusing. What if you put a hole in your conductor? What happens then? Right? Okay. Drill a little, so you have that little gray conductor that the book previously had that had no hole in it. I'm going to take a little drill and drill a little hole in it and see what happens, okay? So it had the same amount of charge, right? That charge just rests on the surface, okay? So what we can do is use Gauss's law again, right? If we use the orange surface here as the Gaussian surface, right, the amount of charge enclosed there, right, is also zero, right? So therefore, the electric field inside that conductor is still zero, right? So if you have a conductor like this, okay, if you drill a hole into the middle, bore a little hole in the middle of it, the electric field inside there is still zero. It doesn't change anything, okay? And this is actually a useful thing, okay, where you, for example, on your phone, okay, what they do on your phone, let me just draw that on the side here, okay? If you peel this little top screen off, you're going to see a little sheet of metal plate. It's usually just a pretty thin aluminum. And the back also, the back plane is usually made of some sort of conductive material, right? So what happened is that, let me draw a phone. If you start peeling your phone apart, okay? Oh, color. Right, let's say this is the back of your phone, right? And what happened is that, let me draw the conductor, right, as a plane of blue stuff. And then the red is the fancy electronic gizmo, the chips, you know, and the resistors and the capacitors, all the electronic goobly gloop that's in here, right? This is the electronic stuff. Okay. But then on top of this, on top of it, you also have another conductor. There's a conductor, okay? And in front, that's where the screen is. If I can draw that in green, that would be nice. Right? This is where the YouTube is, right? Where the screen is. Okay? So the idea is that in order to protect your phone's electronics, right, they put it between two sheets of metal. Okay? This is known as a Faraday cage. Okay? Because what happened is that if you put, if you drill a, you know, just as inside here, there's no electric field inside here, right? I can put my little electronic chip in here, right? And there'll be no electric field that can interfere with it from the outside. Okay? Okay? Right? This is known as electromagnetic shielding, or if you ever go into the elevator in Iraqi, as soon as you go in there, your cell phone stops working. Right? The elevator effect is also known as the Faraday cage, named after this guy named Michael Faraday back in the 1800s. Okay? Because what happens is that, let's say you have this constant electric field. A simple case of a constant electric field is the electric field between two parallel plates. This is what we learned last chapter, right? There's a constant electric field here, okay? Let's say I want to, you know, build my little iPhone in here, right, where it's not disturbed by this electric field. All I have to do is just put it inside a little metal box. What happens is that the electric field is going to attract a negative charge towards the left-hand side and repel or push the positive charge towards the right-hand side. And this is the field line that's going to come out like this, where the positive goes to the negative. So remember, this thing was neutral, right? There was no net charge on it, but the charges got pulled apart. So you actually it still has a net charge of 0, but the negative charge is now more to the left, the positive charge is more to the right. Okay? So this is the field line that it looks like, but inside here you have an area where there's no electric field. So you're protecting whatever, you know, fancy device you have in here using a Faraday cage or a electromagnetic shielding just by putting it inside a metal box. Okay? Okay. There's even fancier video about this. If you ever go on YouTube, you'll see videos like this where people are willing to sit between two very high, we're not going to call that voltage, very high electric fields that creates lightning. But if you're inside a metal cage, you're actually perfectly safe. Okay? Because the electric field cannot get into this cage. Okay? Just because the metal is actually shielding it. Okay? So one hint, I'm not sure how much thunderstorm we have in the valley. We do hear thunder sometimes. So when you're inside your car, you're driving and there's like lightning striking everywhere, it's actually perfectly safe for you to sit inside a car. Okay? It's when you step out of the car and touch the ground, that's when you get struck by lightning. Okay? So whenever you end up in a thunderstorm, sit in your car, don't step on the ground. Okay? because that's when you become a conductor for the lightning. Okay. Let's not deal with the stuff putting inside the charge thing. Anyway, so yeah, so let's do an example before we jump into the worksheet. Okay. So let's say we want to calculate the electric field due to some charged metal sphere. Okay. This metal sphere has a diameter of 2 centimeters. Okay, it's made of brass. Brass is a metal, so therefore it's a conductor. Okay, and it has been given a charge of 2 nanocoulomb. What is the electric field strength on the surface? It's like, wait a second, on the surface, right? Because previously we have done problems like this where, let's do the setup here, where we have a bunch of positive charges, right? That's uniformly distributed, and in your little worksheet today, there's also going to be some weird charge distribution, right? But this is only true if this thing is a insulator, right? Because if it's a conductor, all these charges are going to push each other apart, and the charges will actually move to the surface, right? So this is actually not a true picture if this little sphere is made of metal, which the problem tells you it is. If I can erase faster. Come on. Right. So the charges actually only resides on the surface of the sphere. Okay. Maybe this will be faster. Yeah, it's a little bit better. Right? Does that make sense? Right? If it's an insulator, then the charge can stay in place. If it's a conductor, they're going to move to the edge of the conductor, right? All right. So the question is asking you, what is the electric field, right, on the surface? Okay, what is that? Okay, so you've been given some total amount of charge equals to 2.0 times 10 to the negative 9 coulomb. The diameter is 2.0 centimeters, in other words, 0.02 meters, right? And in a lot of calculations, it's actually more useful to calculate the radius, right? So the radius is actually 0.01 meter, right? Okay. So to figure out this problem, we're going to need to A, utilize the fact that, it's the electric field on the surface of a conductor, right? The electric field on the surface of a conductor was given to us. This charge density divided by the epsilon naught, okay? Okay, but we have no idea what this is, right? How do we figure out the surface charge density? Okay, remember surface charge density is how much charge you have per area, right? The amount of charge per area. How do we calculate that for a charge sphere?
Q over A.
Right, Q over A. Okay, let's do that in blue. Q over A. And what's A in this case? Pi r squared. Well, this is a sphere, right? So it's actually the surface area of a sphere, which is 4 pi r squared. Okay? Okay. So we plug that in there. And then so the electric field is actually Q over 4 pi r squared in the eta hat direction. Okay? So let's punch that in. So this was 2 times 10 to the negative, oops, I forgot the epsilon naught, of course. 2 times negative 9 divided by 4 pi, and r was 0.01 squared, right, because of the square. And this was 8.85 times 10 to the negative 12, okay? So all of this is in SI units, so all the units should work out to be some sort of Newton per Coulomb. Okay, so let's see what this number turns out to be. by 8.85 times 10 to the negative 12. Okay, it's 1.8. I think we can just use 2 sig figs times 10 to the 5 newtons per coulomb. Okay, make sense? Okay, so if whenever you want to calculate the electric field on the surface of a conductor, you just need the charge surface density and just divide that by epsilon naught. Okay. All right. So with that, let me stop the recording on OBS. And who has the popsicle stick? So if you have the popsicle